Welcome to 1007 ICT, 1807 ICT, and 7611 ICT, Computer Systems and Networks. This is Lecture 11, the Transport Layer, Security and Internet Applications. So last time we looked at the network layer and some addressing related issues. We looked at subnetting and then a bit of routing and devices for connecting networks. This time you'll see there's a large amount of content that we're going to cover, which means that we're not going to cover it in great detail. We're just going to cover it as small chunks that together comprise the transport layer, the presentation layer, and the application layer. So again, we're not going to do a lot of process-based stuff here. It's mostly get an understanding of some of these concepts, some of the ideas, how they relate to some of the other things we've talked about earlier in the course. So the transport layer, you'll see that it's layer number 4. It's responsible for getting the entire message from the source process to the destination process. Now if you remember, lower levels were just dealing with packets of stuff, small chunks of the message. This one gets the whole message and it has to get that whole message across from where I am to the other machine, but we're not talking machine to machine, we're talking process to process. So if I'm doing instant messaging, then I've got an instant messaging process here on my computer. It goes across the network, and on the other computer, I get their instant messaging program. So we use a certain technique for that called ports, as opposed to an IP address. The IP address is for their particular address, and when we get there, then we have to look for the program. So the transport layer manages end-to-end delivery between communicating software processes, not computers, but the actual programs on there. And the responsibilities of that layer may include, among other things, segmentation and reassembly or packetizing. I've got a big chunk of stuff. It's too big to send in one go. I'm going to chop it up into smaller parts. Okay, so I'm going to chop it up into, I'm going to say, imagine if I've got a big letter, right? It's like 100 pages. Will all those 100 pages fit in one envelope? Unlikely. Right, so I'll chop it up. 10 pages go in the first envelope, 10 pages go in the second one, 10 in the third one, and so on. How many envelopes do I have? If I had 100 pages, 10 per envelope, I have 10 envelopes, and every envelope needs to have the information stamped on the front of it to say what's happening with this one, right? What's the address? Where am I putting this one? Does that make sense too? Yes? Because they're all going separate ways. So if I segment it or chop it up into parts, when it receives on the other end, I have to put it back together. Right? So I might need some extra information for that. Service point addressing, ensuring that the message reaches the correct process, the program, instant message to instant message. If I have an instant message program and I type in a little message and I send it across and it goes to, I don't know, the calculator. Do you think the calculator can deal with my instant message? No, it's the wrong program, so it shouldn't go there. It should go to the appropriate program. And also error control. There may be some problems between me, the sender, and the receiver on the other end. So we talked about this transport layer example before. We saw this diagram earlier. You'll see that the transport layer, the top one, takes the data and chops it up into smaller chunks. So just drawing that as a diagram, you'll see this is my data. Now this data is too big. It won't fit in the one envelope. My envelopes are only this big, so I have to take some data from here and put it here, some data from here and put it here, and maybe I have to make many of these smaller chunks, depending on how much data I start with. Does that make sense? Every time I do that, you'll see the J and the K, those things. J is my program and K is the program on the other end. There's a number attached to each of those programs. We'll talk about that when we get to that section. So each of the layers does a different thing. At the moment, we're talking about the split into packets part for the transport layer. In terms of error control, before we were talking about on the data link layer, if I'm talking to my neighbor and something goes wrong, I can fix that pretty easily. I know it's between me and my neighbor. I know there's a problem. I'll just send the thing again. If there's a problem between me and the final destination, that could happen inside a network, or it could happen inside one of these machines. So you see here, in that diagram, when I'm talking on my network, well, I can get an error here, and I can fix that so far. We've seen how to do that at the lower level. But I can also get an error inside the router. Is that captured by any network? No. So I need some process to deal with the whole transfer of information, not just in my local network, but also in the parts that I'm not covering yet. If something goes wrong there, I need to deal with that. Okay, so there's a slightly different view of the error detection and correction process there. It's a slightly higher level view. So the transport layer needs to perform error control to handle any errors that occur between the networks as well. In terms of segmenting and reassembling, if I segment something, I chop it up, how do I know when I get them on the other end what the sequence should be? Are they going to necessarily arrive in the same order that I sent them? No, they can go different paths. So some of them may go, if they're more slowly than others, they may not arrive in the same order. That means I need some kind of sequence number, like this is number 1, this is number 2, this is number 3, this is number 4. So when I get them at the other end, I'll look at it and go, this is number 4. Okay, so before this must come 3. Before that must be number 1, and so on. Does that make sense? I can rearrange them. I can't do that if I don't label them properly. If I lose a packet, so I've lost, in this case, it looks like I've lost number 4. How can you tell that you lost number 4? Well, we have 1 of 5, 2 of 5, 3 of 5, 4 of 5 is missing, and 5 of 5 is there as well. So which one is missing? 4. How many are there supposed to be all up? 5. That means I'm only missing 1. Yeah? If I don't have the of 5, I'm not sure which ones I'm missing and which ones I'm not. I don't know how many there are in the sequence. Duplication control is another issue that you get because sometimes you retransmit something. Maybe one of these packets, 3 in this case, was really slow. It took a long time to get to the destination. Okay, by the time that it got there, the destination said, look, I don't think I'm going to get this one, so I'm going to ask for another copy. That happens. So then at the end, you get 2 copies of 3. What do you do with it? You keep the first one and you throw away the second one. Do you need 2 copies? No? Does it matter which copy you use? No? They're the same, so just keep the one you got first and that's fine. So again, you can use the sequence numbers, right, to work out which ones you already have, how many there should be, and whether you should discard something or not. UDP, or the User Datagram Protocol. So UDP is another protocol which we talk about in relation to TCP. So UDP provides a connectionless service with limited error control. There are no sequence numbers, which means that if you lose or duplicate packets, you can't tell. And that seems like a bad thing. If you're sending financial information across a network, you probably want to be able to tell if there's a problem or if you lost something. But if you're streaming some video, for example, do you care that you just missed a frame? Do you want that frame later on? No, so it's perfectly fine in some scenarios. Some scenarios it's not that good. So UDP is pretty good for streaming stuff. Continuous stream of stuff, you lose it, okay, that's fine. You notice it's not very detailed. There's not much stuff in the header. Yeah, there's only a couple of boxes. What about TCP? What can you tell me about the difference between TCP and UDP just looking at the boxes? Does TCP have a lot more boxes in the header? Yes, a lot more, and so it's doing a lot more stuff. So TCP is a connection-oriented transport protocol that provides all the functionality which is defined for the transport layer in the OSI model. The packets are called segments. There's a lot of stuff there. So this thing could be potentially very powerful. UDP doesn't detect duplicates or missing packets. What do you think about TCP? Do you think it has enough information to tell if there are missing ones or duplicated ones? Yes. Sequence numbers in there in the blue, right? So it can track these things. The session layer, now we're moving up another layer, allows 2 communicating processes to coordinate the exchange of data. Establishes, maintains, and synchronizes the interaction between 2 communicating processes. Its responsibilities include dialogue control and synchronization. So dialogue control. 2 processes can communicate in a lot of different ways. They can both talk at the same time. Maybe they alternate talking. Maybe only one of them can talk, right? And you have some setting that you can make for what the communication is. So you have full duplex, both-way communication, half duplex, one at a time, like a CB kind of radio. Synchronization allows a process to define some checkpoints in a message. And so if you have a problem, and you've probably had this, you're downloading a big file, right? If you don't have this synchronization process, then if you download the file and it's like, say, 50 gigabytes, when you get to the last byte, if you have a problem and you don't have this, what will happen? You'll cancel the download and you'll have to start from scratch. If you have a synchronization checkpoint, it just continues from the last valid bit that it got. Does that make sense? So you have a way to do error and disaster control, basically, or recovery. Presentation layer formats the data for interoperability, security, and efficiency of transmission. So we're going through these layers fairly quickly now because we're looking at them fairly high level, but just looking at the key ideas. So this layer deals with the syntax and semantics of the information being exchanged between the communicating systems. It's responsible for translation, encryption, compression. Translation. Have you ever seen a website where the characters on the screen don't look like the characters they should be? You're expecting English, for example, and you're getting some symbols or some other text. Doesn't look right. The encoding or the translation isn't happening properly. And it might be because your browser doesn't support that particular language. Yep. So there's some translation that has to happen in terms of character sets. If you need Japanese characters, you need to make sure that you have the correct encoding for those Japanese characters. Otherwise, they won't show up properly on every device. Encryption. So encryption, that's security. You don't want people to read the information, so you might encrypt it. We already talked about this networking process. If I send a message across a network, everyone on the way can see it. That means that if it's in open, clear text, everyone can read it. Is that always appropriate? No. If you've got banking, like that kind of stuff, you don't want your messages to be open, clear text. So you might want to encrypt it. On the other end, they're going to have to decrypt it, undo the encryption. Compression. We don't care as much these days. We still care, right, about how big files are, and so we tend to zip archive things, for example, or just make them smaller. Use a compression method like an MP3 instead of some other WAV file or whatever. So you can make things smaller. If you compress something, do you need to decompress it? What do you think? Yes, because it's not the actual format that you need, right? So there's something about compression and decompression that happens at this layer. In terms of compression, this is a nice little diagram. I'll just show you a very simple example of compression. So here is a picture. It's a very simple picture on the left here. It's basically a 5 by 5 grid, and it's got some white boxes, some black boxes. Now, it's an animation, let's say, so the next frame of the animation will look like this. So one of the things I could do is I could send all this stuff, which is basically saying for this position it's a 1, for this position it's a 0, and so on. And this is 25 blocks that I have to send. I can send 25 blocks for this one and 25 blocks for the next one, but that's actually quite expensive. What I could do instead is say, well, which ones have changed between this one and this one? Which boxes have changed? This one's the same, changed, same. Yes? Same, changed, same, changed, same, changed, same, changed, same. So how many blocks do I actually need to transfer? All these red ones that are here, these ones, how are the ones that change. So if I just update the ones that changed, I can send a lot less stuff. Does that make sense? So this is a really simple form of compression. You can have much more advanced versions of this. But you can imagine if you're doing an animation, all you want to show is just the pixels that change. The ones that stay the same, you don't need to do anything about. They're going to stay the same on the screen. So this is, as I said, a very simple example, because sometimes it's a bit difficult to see how a compression might actually work, right? Compression basically just means, in this example, you don't send all the bits because you don't need to. You only send the ones that you need to. Security. So moving on to security and this encryption stuff that we talked about before, there's a bunch of different types of securities that we can talk about. So information security requirements have changed quite a bit in recent times, and they continue to change because we're doing a lot more transmission of information, and we're putting a lot more processes online, right, that we didn't used to in the past. So traditionally, security was provided by physical and administrative mechanisms. If you're putting stuff online, you can no longer hide it behind a locked door. You have to do other processes to make that security happen. So widespread use of computers requires automated tools to protect some information that you might store or send. And if you send stuff across a network, then you have to have some measures to protect it while it's being transmitted, and potentially if it's attempted to be read on the other end. So some definitions of the different kinds of security. Computer security is a generic name for the collection of tools designed to protect data and to thwart criminals. Network security are the measures to protect network data during their transmission. You can see a slightly different version of that. Computer system security includes the CPU, peripherals, and the operating system, and as well as the data security. Physical security covers the premises, so actual physical access to this machine. Operational security, the environmental controls, I don't know, like the air conditioning or whatever, depending if you have a server that's going to run hot. Power, equipment, and so on. Procedural security covers the vendor, the management personnel, as well as the ordinary users. This is what you're allowed to do with the equipment. Communication security covers the communications equipment, personnel, transmission paths, adjacent areas, basically all the things related to the communication aspect. You can see there's different definitions for different components, and you might have different strategies for different things. Here is a very basic idea of encryption and decryption. So this is one of the key security techniques that we use. So we have on the left a sender, and the sender has some text, some plain text in English. Now what they want to do is make it so that the people on the network can't just read it. So they have to encrypt it or change it in some way so that it's not just readable directly. Typically that means changing all the letters into some other letters. Right? That's typically what it looks like. And so there's an encryption algorithm, which is that green box, and there's a KE above that, which is the encryption key. This is the thing that we use to turn one letter into another letter. Okay? And it can be different depending on the algorithm and what we're using. That encrypted stuff, all the changed letters, get sent across the network. If I see one of those, I can't read it unless I have a key to interpret it. That's the decryption key, or KD on the right-hand side. So when you run the decryption algorithm, you need another key, typically, to decrypt that information. And when you do that, you get the original text. If you don't have the decryption key, you will never get the real text. You'll just get garbage output. Now, this is a particular diagram that shows the basic concept. Now, sometimes the encryption key and the decryption key are the same. Sometimes they're different, right? So it just depends on the mechanism that we're using. Here is an example of an encryption. So I think probably I'll just draw this one. I think it's pretty easy to see. This is a Caesar cipher, basically. So basically what we've got is my letter A. This letter is number 1. This one is number 2. This one's number 3, 4, all the way up to 26. Okay. If I take my letters and I add 3, what happens to A? A becomes D. B becomes E. C becomes F, and so on. Now X wraps around and becomes A. It goes back to the start. Y becomes B. Z becomes C. So it's basically all the letters have just shifted. Is this easy to crack? It's very easy, actually, right, for us. So there are more advanced versions of these, but this is a really simple way where you can attach a procedure to some text with an encryption key. The key in this case is 3. You add 3. Decryption key is the opposite, subtract 3. Okay, so again, very simple example of an encryption. And again, sometimes it's difficult to see how you could do an encryption, right? But there's much more fancy ones than this, but this is a basic idea. In terms of cryptography, cryptography is closely associated with the field of information security. There's a variety of techniques, and you have different characteristics that you may want to protect. One of them is confidentiality. Typically, You don't want people to read the stuff that you're sending. So confidentiality is keep it secret, and you might use something called cryptography and steganography. So steganography is this idea of having hidden messages. Okay, it's another technique. You may look at integrity. Is the thing that you received actually the thing that they sent, or has someone changed it in the middle? Yeah? Can I check that? I can. I might use something called hash functions to do that. Authenticity. Is it actually from the person who claims they sent it? Maybe someone else sent it and they just used their email address or their name and attached it to it. So you might use digital signatures, message authentication codes, asymmetric ciphers, and so on. There's a bunch of different things you might use for that. And usually you use these techniques in combination, right? But what you can see is, depending on what you're trying to achieve, you might have a different strategy. Okay. Public and private key example. In conventional encryption techniques, security is assured only if the entire process is kept secret. Now that's typically very difficult in a distributed environment. If I'm sending something to my bank, it's going through a network. Everyone on the network can see it. I don't know how I'm going to keep the key secret and keep it with me if it's a long string of numbers, for example. It's a difficult proposition. There are special situations that require different techniques, for example, internet communications and the many senders to one receiver problem, where there's a bank, right? And so basically I'm sending something to a bank and there's many people doing that. So a public key system follows not a symmetrical procedure but an asymmetrical procedure. The encryption key and the algorithm are different to the decryption key and the algorithm. So this is a different type that we're talking about now. Everyone can be given the encryption key, which is public, but only the receiver knows the decryption key. So everyone can encrypt. You can encrypt something and send it, but only the receiver can decrypt it. So only the intended recipient can actually read the message. Okay? And here is an example. So customer 1 has a public key, customer 2 has the public key, customer N has the public key, and they send their stuff to the bank. Now the bank is the only one with the private key, so you can send your message and it's safe as long as the bank is the only one who has the private key. If someone steals the private key from the bank, do we have a problem? Yeah, then that person can read all the messages coming in. So it's important to keep that private key private and safe. Okay. Another relatively new addition to this security part is that the blockchain or the distributed ledger technology. So blockchain is an open distributed ledger that can record transactions between two parties efficiently and in a verifiable and permanent way. Once recorded, the data in any given block in the chain can't be altered after the fact without altering all the subsequent blocks, and that requires a network consensus, right? So it's very difficult to achieve that. So you'll see here that it's configured with a peer-to-peer network, and there's some proof of the work that you've done as you go through, and it keeps track of that. And the nice thing about this is it's very difficult to change history, if that makes sense. Once it's set, right, you can't just go back and change the information, or not very easily. In terms of security management, it deals with managing access to resources, access to the network, might look at an access list, encryption, tokens, fingerprints, bunch of different technologies, techniques that you might have. Access to the physical hardware might be a building and a room key, fingerprints, an iris scanner, whatever the different things are. Maybe you have one of those little USB dongle things that you plug into something. Does that make sense? Yep. So there's lots of different ways to do these. Moving on to the application layer. So we've gone away from the presentation layer. This is the one that you as a user run into and use the most. You interact with the programs, and that's at the application layer. So the application layer allows users, human or software, to access the network. Some important application layer protocols on the internet are email, remote access, file transfer, the World Wide Web, address translation, host configuration. We'll talk about a few of these. Most applications on the internet follow a client-server model. Client-server model basically says that some of the machines are clients and some of them are servers. It's very similar to when you go to a shop, I don't know, like a supermarket, and you go to that deli counter, right, and you take a number and you say, I'm a client, and there's a server giving you stuff. Yep. Now, there may be one server and many clients. Or there may be many server stations and many clients. Does that make sense too? There's lots of different ways to configure that. Most of the common uses of the internet require both a server and a client. The server is the thing that gives you the information. The client is the one who wants it. So typically, as a user, you're the client. Yeah? But there are instances where you may have a client and a server at the same time. It just depends on what you're doing. So a client is an application usually running on the local computer that asks for information. And a server is usually running somewhere else, always, and you ask it for stuff. Many clients can access the services of one server, and a client is run only when it's needed, while a server has to be running all the time because you don't know when you're going to get those requests. Okay. We have fat clients and thin clients. So the fat clients perform all or most of the processing, so they have a big job. The thin clients perform little or no processing for themselves. So here's a difference, and you may have seen this, say for example, on a game that you have. Maybe your machine, your computer is running all the graphics code, right? All the environments, drawing all the pictures. That's not done across the network because it would be inefficient. But what's happening is if it's an online game, maybe it's sending a little bit of information to a server saying, I just moved one step forward. Or I shot my gun, or I picked this up, or I did whatever it is that the game lets you do. And so that might be a fat client. You're doing a lot of the work, and the server is doing a little bit of the work. As opposed to the thin client, where it's just an interface. You just press a button, and all the information goes through to the server. So if you imagine that a thin client might be something like an EFTPOS terminal, where you have a card reader, and all it does really is just scan your card and get your input, and all the information is sent to the bank, and the bank does all the work. It doesn't trust the terminal, right? Okay, so different models are used for different environments. Servers can be mainframes costing a lot of money. They may have network accessible storage. They might be personal computers. They might be clusters of personal computers, right? And depending on what you're trying to achieve, you may have, a range of these. Your home computer, if it's running Windows, is probably running some servers of some kind. Does that make sense too? Right? It has some services running, right, to do that stuff. So client computers can be terminals, DUM, transaction point of sale, personal computers, network computers, special purpose terminals. Lots of different things can be clients. Anything that can get you an input basically could be a client of some kind. We talked earlier about on my computer, when I send a message, it has to go from my program, like Instant Message, to another program, Instant Message, on the other machine. The way that's dealt with is that each computer has a number of port addresses. So they have 65,000 roughly port addresses, and each of those port addresses can be assigned to a program. So if I'm the Instant Message program, I might say, look, I'm going to take port 10,000. If you want to communicate with me, you need to talk to port 10,000. You can think of it as like a PO box, like on the post offices where they have the big wall of post office boxes, and they all have numbers, right? If you have a letter for someone, you put it in a particular numbered box, and that person grabs it from that box and uses it. It's a very similar idea with this. These are called port addresses, and you have a big bunch of them, and a program will be listening to a particular port to be able to get that information. Domain name system. So every computer or host on the internet has a name and a numerical address. Now last time we talked about subnetting and the IP addresses. And I mentioned, I think at that point, that we typically don't work with IP addresses. We work with English versions of them, like www.google.com. Yeah? You can certainly use the IP address version of that, but it's difficult for us to remember. What that means is there must be a translation between me typing www.google.com and the actual IP address. Yeah? Because the machine uses the IP address. Do you do the translation? No. There's a program or something sitting around that takes your text, your English text, and turns it into the IP address. So that DNS, or the domain name system, is the thing that does that processing or that translation for you. So the idea is for people to use computer names and to let the computers and the routers work with the IP addresses. Is more efficient for them. So DNS names are constructed in a hierarchical naming fashion, read right to left. At the right is a two-letter country code, followed by a domain name, followed by the organization, followed by the computer name. So for example, griffith.edu.au, the .au is on the end. So AU is Australia. EDU is educational machines inside Australia. Griffith is one of those educational institutions in Australia. And then you might have, I don't know, a machine name like fred.griffith.edu.au. And Fred would be a machine inside that domain. So if I'm attached to Fred and I want to go to, I don't know, google.com, is google.com inside griffith.edu.au? No, no machine inside Griffith knows about that. So it says, okay, I don't know about this. Who is my parent? I'm griffith.edu.au. My parent is .edu. I'll go up one level and ask the big .edu machine who knows about all the .edu things, do you know about google.com? And it says, nope, they're not here. What's the next one? griffith.edu.au. We need to go to the .au one. And the .au one says, okay, that's not me either. I need to go outside, and actually I need to go to the US, probably, and go to google.com, to the .com framework. Does that make sense as well? So we basically go up a chain, and then eventually we go back down a chain. Make sense? So what that looks like, just as a diagram, let's draw it on this one, I think. So as a diagram, what that looks like is I've got Griffith, and then over here I've got EDU, and then over here I have AU, right? And then apparently google.com is not here. I asked this guy, it's not here, it's not here. So now I need to go to .com. Yep, and in .com I have Google. What other .coms do you know? Amazon. Yeah, there's a whole bunch of these .com things, but I need to get to the .com one first so that it can go down to the right environment. Okay, so that's the idea of the DNS. And there's a bunch of different domain names, .com, .edu, .gov, .au, .new Zealand, .uk, and so on, right? So there's a different range of those. And what that allows us to do is it allows our local machines to only have to worry about our local machines. Do you think my laptop is powerful enough to be able to know about every single computer on the internet? Not even close. So it's not its job. Its job is to say, okay, I need to go somewhere. Who knows? Someone further up knows a bit more. Someone further up knows a bit more, and so on. So it's a nice way to structure that. DHCP is a way to configure some information about the computer. So all computers attached to a TCP/IP internet have to know some information. They need to know their IP address, a subnet mask, we talked about that, and the IP address of the nearest gateway or router to get packets outside of the current network. Because I don't necessarily just want to talk to my own network, I might want to talk to people outside. So there's a machine that knows how to do that, and I need to know its address. And I also need to know the IP address of a name server, or the DNS. If I want to look up some of this stuff, I don't know that information. The DNS server will know, right, that information. You can set all that information manually. You can certainly do that, and you probably have done that at home. You know, you open up the little panel, set it up. Imagine, though, if you are the person responsible for the Griffith Wi-Fi network. How many Wi-Fi connections are there in Griffith every minute? What do you think? 1, 2, 1,000, 10,000? There's a lot, right? Do they change very frequently? Can you imagine trying to update the tables every time there's a new connection? It's not really feasible, right? So there's an automated way to do that. And so DHCP is the thing that lets you do that. And typically it's useful in a network where the information is changing, right? So DHCP can automatically provide this information. There's two modes of operation. Information for each computer on the network is stored in a table along with each computer's physical address. And every time a computer is switched on, it receives the same set of values. Do you think this is what happens with the Griffith Wi-Fi network? That you always have the same IP address? No. Why not? Because they don't know who's coming. Does that make sense too? So what they probably do is the second one. Each time a computer connects to the network, it's given the next available IP address from a big pool of these IP addresses, and you get a random one basically every time. Does that make sense? That seems a more reasonable approach for this environment. If you had a much smaller network with only 5 computers on it, Maybe you would pick the fixed one, right? It just depends on what you're trying to achieve. And DHCP is also often used to allow a group of hosts to share a small number of IP addresses. And you may do that at home, for example, right? So there's different uses for this approach. VPNs or virtual private networks, you probably have used these already at Griffith. So if you're outside of the university and you want to access certain kinds of resources, the university requirement is that you are on the local network. Now, if you're outside, you can use a virtual private network to pretend that you're on the local network. It means you have to log in, you have to use some software, and it's like you're actually on the local network. That's basically what a VPN does. It basically creates a tunnel from where you are to the network, and it's encrypted, so it's a safe passage of information. It can ensure the safety. Email. I don't think I have to say too much about email. You'll use it. But basically, it's sending messages using the Simple Mail Transfer Protocol, or SMTP. And there are these message transfer agents, user agents, and so on, and they communicate with each other to get these messages sent around. It's actually a lot more involved than it looks. Like, from our perspective, we just see a program where we type some stuff in, we hit send, and it's gone, right? There's a bit more going on underneath. This is kind of what it looks like. So the sender, there's a user agent, there's a message transfer agent, and it sends it across the network, and then there's a message transfer agent server on one end, and there's a user agent which gives it to the recipient. So it's a lot of little steps going through. For our purposes, all that's really happening is I'm sending some text usually, or a picture or whatever, across a network. Okay. Originally, this process could only cope with ASCII text, which was fine when it first came out, but pretty soon people want to send pictures, audio files, whatever, and they couldn't do it because ASCII text doesn't have facility for that. So if you want to send pictures or audio, you have to do something else. And basically there's this thing called the Multi-Purpose Internet Mail Extension, or MIME. You have these MIME types, which you may have seen in some documentation, and it defines a way in which different data types and formatted message bodies can be converted into a document made up of ASCII characters. Basically, it encodes it as ASCII characters, and then on the other end it says, okay, this set of ASCII characters is a picture, or it's an audio file in this format, right? So then when you get it, you convert it back to that format, but you've sent it as ASCII. Okay, so it just compresses it basically into that. So when the message reaches the other user, their client has to be able to translate it back. And if they can't, all you see is just a bunch of text and symbols, right? The post office protocol. People still use this, but probably a lot of the cloud-based web services are starting to get around this a little bit. But basically, in the old days, you would have to log on to a mail server. Then you'd have to use the mail server software to read, edit, and manage your email messages, which may or may not have been a pleasant user experience. Right? It really depends, but it probably wasn't that nice an experience. So on your own computer, you have a window, you have some nice buttons, you have all this kind of stuff that makes it a bit nicer. POP allows you to download stuff from the email server, so you can just download it to your particular computer and work on it there. That's good for the server because it's not having to do all the mail stuff. Right, you're doing all the editing on your machine. It's good for you because you have a copy of the email. Right, you don't have to log on to it. You have access to it all the time. Probably we're moving towards the cloud and the IMAP kind of model, which is another model where you have folders and things on the environment that you're working in. So let's say through a web-based client. But there is still a use for the POP environment to download stuff to a particular computer. Moving on to remote access, so you have different ways to do the SSH and Telnet, and one of the goals of the internet, or main goal really, is to let users access the resources of other computers or networks. Often client-server software exists to provide that access for common applications, but it's impractical to write special programs for every single thing that you would like to do. So we have this idea of remote access. Has anyone ever used a remote access technology? Yeah, there's different flavors of them. Some of them are Windows based, some of them are like a DOS environment, right? Using SSH or Telnet, you can take control of a computer that's not where you are and give it commands. Okay, so this is what it looks like. There's a remote terminal and there's a virtual or local terminal, goes through a Telnet server and a Telnet client, And what you get, if you use this, you get your local computer character set, the one you're used to, and there's a translation to this generic character set that everyone can understand. Do you think that everyone has the same type of keyboard? No, there are different languages, different organizations of those things. So the encodings need to be the same if we're going to talk across multiple machines. And so there's some kind of local computer character set that you're working with at your end, and then there's a common character set in the middle, and then it has to be translated back to the remote computer character set on the other end. Telnet is the non-secure version, SSH is the secure version. So these days you should be using SSH. Okay, remember what I said before about sending messages across a network? If you're using Telnet and it's not encrypted, you have to use a username and a password. Your username and password are being sent in plain text across a network. What do you think? Is that safe or not safe? It's not safe at all. It means anyone in between can just look at your username, your password, and they can get into your computer, right? So you want to use a secure version. FTP, I'm sure you've used it in some form, even if you're not aware that you've used it. It's the way to transfer files between computers. And it solves a lot of different problems because different computers have different file name conventions, different directory structures, different character sets, different file types, and so on. FTP works by establishing two connections. One is the control connection, get, put, those kinds of commands, and the other one is the actual data. So what you do is you separate the data movement from the actual commands, which means you can still send commands while you're doing the transfer. And this is what it looks like. So you'd users there's a user interface. It could be text, it could be a window, right? Usually these days there's a window on the left and a window on the right, and you just move stuff backwards and forwards, but it could just be text. There's a control process and a data transfer process. The port 20, remember the port numbers we used? Port 20 is predefined for the control path, and port 21 is used for the data path. Which means that FTP is a predefined protocol. That means that port 20 and port 21 are not ports that you can use for your own programs because they're defined as ports for FTP. And there are a lot of these other protocols which have their own port numbers associated with them. World Wide Web. Again, I don't need to say too much about it. The nice thing about the World Wide Web is that it allows us to have a page with links in it that we can follow to other resources. And what that means is we don't actually need to know where things are except for where the starting point is, if that makes sense. And we also have search engines where we can just type in a search query and it will give us the starting point. Before this, you needed to know the name of the computer, you needed to know the directory, you needed to know the file name. You used to have a username and a password on that computer, and if you didn't, you couldn't access that resource. Is that a lot more limited than what we have with the World Wide Web? Absolutely. So this is a big improvement, and we're very used to it now, but there was a big difference between what happened before and afterwards. HTTP, or the Hypertext Transfer Protocol, is the protocol for the web. It runs on top of TCP, so it runs on top of the internet. And many people believe that the web is anonymous. It is totally not anonymous, because if you ask for some resource from somewhere, it must know your address to send the response. Even if you use obfuscation technologies, right, to sort of pretend the address is different, at some point there has to be a connection between you and the endpoint. If there isn't, you can't get the information. So there is no such thing as anonymity technically on the internet or the web, but you can obfuscate things. In summary, for this section, we looked at the transport layer, the application layer, and then internet applications. Next will be revision, and that's the end of this section.